Hey, today I'm going to talk a little bit about the setup procedure for the VistaClare Dart NMR probe. The things that you will have, I've taken everything out of the box, but you'll look a little bit different when you get the boxes. There are two batteries, look like this. There's a probe, so this has strong magnets in it, so keep it away from your wallet, your cell phone, and pacemakers. There's the cable. And it says minimum bend radius of 12 inches, so never roll it any tighter than 12-inch circle. And then you have to be really careful of the cable head here, that this also doesn't bend too far. It's kind of heavy, so it's easy for that to happen accidentally. You'll need the computer, and then you'll have the control unit. So in the control unit, there'll be this is the data cable, so this is what's going to connect the control unit to the computer. And the first thing we want to do is put the batteries into the instrument. So this plate here is held on by 4 screws I've already taken off. And inside the battery hole, you just put the 2 batteries like this. And then each of the connectors just clicks on. So at this point, the control unit's set to go, and we're going to set up the probe, and then we're going to set up the computer. So when we do the connection to the probe, the best thing to do is put it down on a tarp if you can, and then just do the entire connection with everything resting on the ground. And that's mostly because this avoids a lot of risk with accidentally torquing the cable head too much. So we'll just make sure there's no dust and debris. You're pretty clean. You can take off both caps. You want to look in the top of the cable head beforehand. Just make sure there's no dust and debris in there either. Keep track of these caps. They're a little bit easy to lose, but I find that if you stick them together, at least you're only kind of trying to keep track of one thing. So the cable head, when you look inside of here, you can't see it right now, but you can see there's an O-ring, and you just want to make sure the O-ring is flat. And so the other thing is that inside the cable head there are 2 little bumps that key the direction of the cable head so that the probe connects it correctly. And there are 2 slots on the probe, you can see right there and there, that fit into those bumps. So never rotate the cable, always just rotate the probe. And so it's easiest to just look in ahead of time and see kind of which direction those bumps and slots are. And then once you line them up, then you can screw it on. And it will very quickly pull the probe towards the cable, and so you know you've done it right if the probe and cable are well connected. The next thing we're going to do is connect the probe to the dart and just do a test measurement to make sure that everything is working properly. So often the best thing to do is start turning on the computer now. Takes a minute to boot up. And then just take these cable ties off. So once the cable is unwrapped, it's really important that we respect the cable extremely highly. This is it's very strong cable in the direction of gravity when you have it down a well, but it's not very strong in terms of bendiness. So we want to make absolutely sure it doesn't get kinks. And so anytime we're uncoiling it, just be extra careful that nothing gets bent past that 12-inch bend diameter. And so in order to connect it to the instrument, all you need is maybe a meter or so at the end, and you're looking for this, the floppier part of the cable with the little extra connectors. And so these are the Milspec Amphenol connectors, and it's a little bit counterintuitive. You actually put your fingers on the barrel below the top of the gap, so below the blue line, and just spin the bottom part of the barrel and the top pops off. So if you try to actually just twist the little top cap, it won't ever come, and that's actually an easy way to break it. So what you need to do is just grab below the blue line and spin that, and the top will just jump right off. So on the control unit, there's a little marker for sensor. These cables are directional. You can't hook it up wrong, so don't worry about that. But you're looking for the one labeled sensors, and again, this is a keyed connection, so just look before you push it into which direction is going to fit for that set of notches, and then push it down in place, and then again just twist the blue ring, and that will connect it up. So the next thing is your data cable, and so this is another one of these Amphenol connectors that's keyed. It just has a USB plug in it, but there's a USB connector on top here, and so all you have to do is find the key, and then twist the connector on again. And obviously last, it just goes to the computer. Okay, so once you start the computer, it's going to look like this. There's a big sort of ball-shaped icon in the middle that says Dart Only. Once your USB plug is already plugged in, then you can click on the Dart Only and just press the power button on the control unit. And once you press the power button on the control unit, the power button ring will glow green, and the computer will make a little sort of clunking noise. So the next step is to select the calibration, and on the desktop there is a file that says Dart Calibration Folder Path, and that path is where you need to go. So select folder, in the folder VistaClare NMR data. Currently it's in Dart 2017, calibrations. And then you just double click all the way into the folder, and you'll see down here the folder name will say Cal DDC U6 Dart 6 33 meter UI. But nothing will show up in the folder, but that's okay. You can just, once it says that folder in the bottom, then you can say select folder. And from there you can just say done. So now that we have the probe plugged in, the instrument on, and the computer ready, it's not in the well yet. The probe is not in the well. So the first thing we can do is just check to make sure it's all hooked up correctly, and you can just press the ping button that shows on the middle of the screen. And what you're looking for is for this to be a nice clean peak in both of these bottom windows, and then a lot of high amplitude signal followed by no signal in the time window on channel 1. If it looks anything different than this, then that's a problem. And you can ping also the frequency too, and it'll show up as a slightly different peak. But basically the same idea. You want these to be clean peaks and then a clean time series. So once you're done with that, then we can move on to putting the probe in the well. So here's the tripod and shiv wheel. Again, the one that you are using will likely look slightly different than this, but the concept is the same. There's gonna be a fork, there's gonna be some kind of wheel, and you'll be using a surveyor tripod. It's really important that you make sure that the ends of the legs on the surveyor tripod are firmly pushed into the ground, because that's going to make sure that the legs don't just splay out. And then you want to take a few minutes to really carefully be sure that the shiv wheel, this in this case the bicycle wheel, is lined up over the well. And so what that means is that the line tangent to the normal vector on that comes off of this wheel is going to come straight into the top of the well. So I lined it up ahead of time, and it looks pretty good for right now, but we'll have a double check once we actually get the probe out. So get your well ready, whatever you need to do, and once your shiv wheel is lined up, your tripod is firmly in place, and your well is ready to log. So if you have any sensors in it, be sure to take any sensors that might be in the well out. Next, I'm going to bring over the probe and put it over the shiv and into the well. So it's very helpful but not essential to know how deep your well is ahead of time, and it is essential to make sure there's nothing blocking the well. And that actually includes the well casing itself. So if you imagine this is a well casing, if it's put in a well that deviates from vertical, then the well casing will be slightly bent. And as that probe tries to go through this very close fitting well casing, it will get stuck on that bend. So you want to run something down the well ahead of time just to make sure it's clear and so you know how deep it is. The best thing to use is something that's long and skinny, because that will find those any sort of large radius bends in the casing. But we use this. This is just a piece of PVC pipe that we attach to a rope and then put down the well to make sure it's clear, and then bring it back up so we know also how deep it is. So keeping in mind this large bend radius that we need to maintain with the cable, this is when it's at its most delicate. So what I typically do is either with 2 people or 1 person can do this with a hand above their head. Just always keep that the length of wire right above the probe head just up in the air. Now at this point, of course, if you were to let it go, it would just, gravity would take the probe to the bottom of the well, so we want to be really careful. Again, this is a job that's handy to have 2 people for, but as long as you keep friction on the cable as you let it slowly down. If you don't know how deep the well is, then you have to be really careful that you don't just slam the probe into the ground at the bottom of the well. So I happen to know this is a really shallow well because I just installed it yesterday. So that's it. It's only about 2 meters deep. But if you have a well that's drilled into rock, or it has a hard bottom and you don't know where it is, just really be very, very slow as you're putting the probe into the well. And now last, we can just double check that our sheave wheel is nicely aligned. And I'm just looking down here and I can see that it's going pretty straight into the tube. It's a little bit off to one side, but it's not too much of a problem. And rather than mess with it because it's so close to being perfect, I'm just not gonna change it. So in order to keep the probe in one place while we measure, we use this as a brake. It's a prusik, and it's 2 lengths of rope connected to a carabiner. And so all you do is you take the length of rope off and keep the knot sort of on the side like this, maybe a little bit down towards the bottom, and then loop the rope around the NMR cable, but through the center of itself. And so what you'll end up with is this. It's basically 3 little loops around the wire, and then the 2 other loops that have the knot in it will come right around the center of the knot. And so once you have that in place, then all you have to do is put that in your carabiner. So the way this works is that anytime that there's tension on the cable, it's automatically going to create friction through this rope. And so now it can't go down the well. It can only go once you move the prusik. And so the prusik, all you have to do is basically take it in your hands and collapse it, and then that will let it move through. So you can move it down in that direction, or you can move it up just by sliding the prusik up the cable. And then when you're in the right spot again, it'll automatically just grab. Okay, so now that the sensor is in the well, it's at the bottom of the well, we can go back to our computer and open up that logging software again. And this time we're just going to go over to the logger tab. And we're going to set a few things. We're going to set the measurement increment, and we're going to set the measurement parameters, and we're going to give it a file name. So the file name, we'll start with the file name. And if you just go to this red bar on top and click the folder right next to it, I suggest saving everything somewhere in the VistaClare NMR data folder. You're responsible for your own data, so make sure you grab it. So next we can adjust the increment, and it kind of always automatically comes up as a 1/2 meter increment, but typically with this tool you'll always want to do a 1/4 meter or 25 centimeter increment. because that's a nominal resolution of the measurement. The next thing is the duration of the setting the measurement sequence. And you can just use the sequencing file. That's just going to be these parameters automatically put in there. Typically, I increase the number of averages on the long wait time. So the top TR is your recovery time, and so the long one is 1 second. And so these are for longer water that's going to be in larger pores or bulk water. So I usually increase the number of averages on that. It makes it take a little bit longer, but I think you get better data for those longer relaxation times. And if you have a reason to do something different, then we probably would have discussed it before. So aside from that, that's a pretty reasonable place to start with settings. The next thing is to start it. So again, we're logging bottom up. You might not log from bottom up. You're allowed to log from top down. I just log from bottom up so that the sensor's already at the top when I'm done. It's not really a big deal whichever way you do it. So we'll press the start button, and as soon as it starts, you'll see this some blinking going on in the corner here that says what stack number it's on, and then you'll see the data here. And this data doesn't really mean a lot the way it's displayed, but as long as you see something that looks like this with a bunch of sort of like sporadic spikes on it like this, then everything is fine. So each depth level of the well with these settings will take about 7 minutes. The time estimate on the screen is a little bit too short for what it actually is. And then once that depth level is finished measuring, then the instrument will beep and it will tell you to move your sensor up 1 increment. And so that's our cue to advance the location of the sensor. And you can see that it says move it and then say OK to continue. So we need to move it first and then we'll press that button. So now that we have the sensor advanced, just press continue, and then it starts the next measurement. And then you repeat that until you get to the top of the well. So a couple of minor notes here. One is the instrument, the surface station, I'm keeping about 5 meters away from the instrument, and that's kind of an average good distance. If you can keep it farther away, that's fine. Of course, the total cable length is only 33 meters, so there will be a limit depending on how deep your well is to how far away you can keep it. But that's just to reduce the potential for noise to interfere with the measurement. Probably the most typical source of noise on this measurement will be lightning, unless of course you have, like, you're right near some infrastructure with power lines or cars or whatever like that. So we don't usually use the noise reference cable in remote areas, but you can use it, and it's really obvious. It's just a gray cable. You plug it in on the instrument where it says noise reference cable, plug it into the noise reference cable box, which is just a big gray square box, and then put that in the direction of the noise. The last thing is that the sensor itself, it's really the bottom of the sensor that's detecting where the water is. Not all the way at the bottom, but just slightly above it. So when you see your sensor start to come out of the top of the well, you want to make sure that the bottom of the sensor is also completely out of the ground, particularly if you're going to be measuring the near surface moisture content, if that's important to you. So what I usually do is I usually do one extra depth interval that's either across the ground interface or even just above it in the air. Because if you measure it and it's just the air signal, there's no NMR signal, then you know you haven't missed anything in the well. So if you want to be sure to get everything, that's just an easy way to do it. It takes a little bit longer, but you know you don't miss anything. All right, so once you have the first measurement, it's nice just to check it out and make sure that the data looks good. So for doing that, you'll go to the top of the screen here. It says Javelin processor in the middle top, and it's okay that it doesn't say Dart. Same program. So you can launch the Javelin processor. You're going to go find your data file, and So there'll be a whole folder full of lots and lots of, well, depending on exactly how you're making the measurement, there will be more than one LVM file. So the LVM is the raw data file. So what you want to do is just pick the top one on the list, and then when it says file indices to process, if you've already measured one or more additional levels, then there will be more numbers here. So easiest just to pick the first one. So just say file indices to process 1, and that's it. It will ask you if you want to process multiple wait times together. Always just say yes to that. And you do not need to use DC voltage scaling. Say no to that. And then it will automatically go through some more steps and give you some figures. So when it asks you again to use DC voltage scaling, you can say no. And when it asks you to save it, we're just looking at the data to make sure it's okay, so you don't need to save. You can just hit cancel on that. And then you can minimize the processing menu. And the figures that we want to look at are this one with the multi-exponential fit, and then the spin echo train, and you don't need the other ones. So what we're looking for is for there to be signal that is exponential decreasing from left to right on this top plot. And so the red line is your data, and the green line is the fit to the data. And so what this is showing us is that the initial amplitude is around 28, maybe 30% water content. It looks like it's actually 33. And then it gives you a T2 mean log relaxation time and an estimate of noise. So this estimate of noise is probably the first important thing to look at. This should hopefully be around 4%, maybe a little bit less, and not much more than 5 if you can avoid it. If it's much more than 5, then you need to do something to improve the data quality. The next thing is just to make sure there's an exponential fit. You'll notice that the data quality in the early times is actually much better than when you get out to late times, and that's a function of using this multi-wait time acquisition strategy, and they actually just get pasted together here. So you get really high quality data for your short times, and then you can tolerate lower quality for your long relaxation times, because that's going to give you more points along that curve fit. And the bottom is going to give you your T2 distribution. Again, so anything under the smaller size is going to be, the smaller relaxation time is going to be smaller size pores, or larger size over here on the longer end. The spin echo train, what you want to see ideally is going to be bright colors, and then sort of decreasing to lighter or blue colors down at the end. This happens to be a really clay-rich soil, so there's only signal right in the first 10-ish nanoseconds. On the right side, if you have good coherence, then this will all be the same color. So you can see sort of we have good coherence in the first 10 nanoseconds, and we have a little bit of signal in the first 10 nanoseconds. And it's kind of noisy in the later time, and so we have poor coherence out here. So we could see the exponential in the time series, so we know that our data is fine. This, if it was wetter or if it had larger pores, would look a little bit nicer, but you can look for some other examples of that. So we're satisfied everything's going fine, so we just close the processing program and continue logging.